So for part 2, we're going to be doing binary search trees. So in part 2, part 1 says to draw a binary tree after an insertion of the following elements in order. So we have 60, 40, 35, 75, 20, 100, 25, and 70. So we'll start at the root at 60 right here, and then go down the line. So 40, 35, 1, 20, 25, 75, 70, 90, and 100 right here. And for the next part, it says to also draw the binary tree after insert the following elements order for the second one. So I'm gonna do that one right here. And those elements are 10, 20, 30, 40, it goes up to 100. 70, 80, 90, 100. It's a funny one. So part 3 after that says explain what differs in the above two trees, specifically address how many leaf nodes there are, the depth of the right and leftmost nodes, and the height of both left and right subtrees from the root node. Okay, so so we're gonna address how many leaf nodes there are. So for the first one that we did, first let me draw the second one. Totally forgot. There's a fly here. And the reason it looks like this is because every preceding element is going to be the right child of the last. So back to what I was going to say about number 3, we're going to address how many leaf nodes there are. So for the first one here, leaf nodes, there will be 3 leaf nodes because 70, 100, and 25 are the 3, and they don't have any children. And for this one, number of leaf nodes, there is only going to be 1 child for this because there will only be 100 right here. And then we're going to address the depth of the right and leftmost nodes. So for the first one, the depth of this one will be, for the rightmost node, will be 3 because it goes down 3 from the root. Same thing would be for the leftmost node. Depth would be 3. Going down to this one would be the depth would equal 0. Well, for this one, there would be no leftmost node. There's only going to be a rightmost node. So continuing on, we'll do the height of both the left and the right subtrees from the root node. So I'm going to do the height of left right subtree. So the height of the left of this one would be 5 because it's going back to the root would be 5, 2, 3, 4, and 5. I'll just circle that just to make it clear. The height of the right side would be 3, going back up to the root. 1, 2, and 3. Going down to this one, height of left, height of right. So since there is no left side, the height of the left would be 0. And for the height of the right, this one would be 9 going back up to the top to the root. So it'd be 1, 2, 3, 4, 5, 6, 7, 8. Well, starting right here would be 9. So that's it for number 3, and I'll get a different page for number 4. So 4, if a binary tree is complete, does that necessarily mean it is also full? Justify your answer with drawing of trees. So a binary tree is full only if it has exactly 0 or 2 children. So I'm gonna show you an example right here. So if there were to be a tree like this, and like this would be a complete tree. An incomplete tree would look like this. The reason why it's an incomplete tree is because the left node on this side still has space for more children. And going back to what the question says, no, that does not necessarily mean it is complete. Binary tree is complete if all levels are full except possibly the last level, which must be filled left to right. Okay. And that was it for the binary search trees part 2.